So everyone, thank you very much for joining us at the webinar here on fracture mechanics and engineering critical assessment, where we're going to have a look at these two topics today over the next hour. And could I just get Mehdi? Can you see the screen? Can everyone hear me?
Yes, I can, Eric.
Okay, great. Thank you. So just a little bit of housekeeping to start with. There are a few people in the meeting, so if you could just keep your microphone on mute for the majority of the time, that'd be great. Now, if you have questions, please feel free to write them in the chat. After we're going to have a break after the first presentation and then after the second for questions. Now, if your question is something that you don't want to share to the large forum, you can write the question to my colleague Mehdi. His email is here, meba@force.dk, or really get in touch with any of the Force people. And please provide your name and contact details that if we don't get to all the questions during the session, that we can follow up with you after, because we don't want to leave any questions open. So just to move along, there are three people from Force here today. Myself, my name is Eric Putnam. I'm head of department for the materials, component, and structure testing teams. We have Rian Holdstock. He's a project manager within materials testing. Rian will be giving the first part on kind of the background and basics within fracture mechanics testing. And then we have Mass Holm, who's a specialist within our engineering consultancy area. And Mass will be going a little bit more on the engineering critical assessment and the link into the testing programs. So that is the end of my part, and I will now pass off to Rian, who will go into fracture mechanics testing. So Rian, I'll stop sharing, and you're muted, Rian.
There we go. Thanks, Eric. Right, let me just share my screen here. There you go. Okay. So Eric, can you see my presentation?
We're good to go, Rian.
Okay. So then
you just need to make it full screen.
Yeah, there you go. It should start now. Does that work?
We're all set.
Beautiful. Okay. Well, welcome to today, and thanks for the introduction, Eric. And that's pretty much what I'm going to do today. Is I'll just give you guys an introduction to things. My background is welding and metallurgy and fabricating and testing big things. I'm not a specialist in fracture mechanics in any way, but I've seen it being used in industry, and I'm involved with it now and again. But it's pretty much like a car, you know how to drive a car, but you don't know how the thing works. You just know, get in, put the key and turn the ignition, off you go. And that's pretty much the same as me. But what I will try and do is explain a few of the things that I've seen. And my big aim is to build a bit of background for what follows next, afterwards with the next presenter, when Mass will tell you the other things. Right, so the agenda is basics. The basics of fracture mechanics, basics of fracture toughness, how do we test for fracture toughness, and also I'll just introduce this engineering critical assessment. Now, before we build something, we need to go through paperwork, and I'm sure most of you probably already know this. So the example we can see there are some specific rules that tell us about the flaws in the structure. And one important thing is that it talks about a maximum flaw size. Now, these things are mostly conservative, and as we know about conservative things, it makes things more expensive, and it also slows down the work. Oh. Then we ask the question now, is there an alternative? Is there a safe alternative? What can we do? And that is the theme of today. So I will introduce the basics, and then hopefully that if you don't already have it, it'll give you a little bit of an understanding of how we can go about using a safe alternative rather than using the conservative approach given by the codes and standards. Okay, so in case there's some of you who are very new to this, I'll start very basic and I'll ramp up a little bit. So let's introduce the word brittle. And what does it mean? Very basically, very easily, it takes something and you bend it, or you're trying to bend it, and if it snaps, it's brittle. Important thing is there was no deformation. Then if we look at ductile, we see the opposite. There is deformation, and it did not snap during bending. So this deformation, that's the word that I'm starting with. If there's deformation, this is going to take us into the fracture mechanics part. Now, here is an industry example of a brittle fracture, and we can see that around where the fracture was, there was no deformation. So that is a very easy way to see that this was a brittle fracture. If we go to a ductile fracture, we see this pipe here. There is deformation, and so very easily we can see one was a brittle fracture and the other one was ductile. Okay, so that was easy, but now I also have to separate impact toughness from fracture toughness, and they are not the same thing. Impact toughness gives us a fast fracture and gives us a quick general assessment. But if we want to evaluate a material's fracture toughness, we need to go a bit more deeper. We need a lot more work. And the example here shows a typical setup for fracture toughness. If we look on the right-hand side, the specimen will be pulled apart. We throw in some mathematics, close control of the loading conditions, the specimen geometry, and that little black thing there that measures how the crack grows, or not the crack grows, but it measures how the mouth, the front of the crack, or the face of the crack is opening up. And we do some analysis after the specimen has fractured, and very simply that gives us a basic description of fracture toughness. So of course impact toughness on the left is just put something, put the specimen in there, release the striker very quickly, it fractures the specimen. That gives us the impact toughness. Whereas the fracture toughness, we need to look at what's happening more closely at the crack tip. Okay, a typical test specimen. Here we see a compact tension specimen. Now, as the word says, it's tested in tension. The specimen geometry is important. So things like width, height, length, these have to be closely controlled. We also see that there's a machined notch, and sometimes there's a fatigue pre-crack. So here's our machined. Hi guys, just mute your microphone there, please. Unless you have something really important to tell me, if I can just ask you to mute your microphone. So if you look at that drawing there on the left-hand side, there's a machined notch, and then there's a small straight black line. Sometimes there's a fatigue pre-crack put in there, and what that does, it helps us to have a very accurate starting condition for the test. Next one to consider is a single-edged notch bend specimen, or SENB. It's bigger than the previous one, the CT specimen, and the other one was in tension. This one is in bending. But just like before, the geometry and the starting conditions are very important. the final specimen that I want to introduce, which of course is, these are not all the specimens, it's just the 3 for today that I want to introduce to you, is a single edge notch tensile specimen. So it's a tensile test, but with a notch, and it's also relatively thin. And remember there that the geometry is important when we have to decide, or when we have to design a fracture toughness test. So I'm throwing in words like geometry because this we'll see later where this comes from. Okay, now let's have a quick look at fracture mechanics. Now these are my words. As I said, I'm not a specialist. I'm just giving you my understanding of it. So fracture mechanics uses mathematical methods to describe the force needed to start a crack, and also the resistance of the material to the growth of that crack. So when does a crack become a problem? This example here, if we look at that in the middle there's something called a stress intensity factor, and it's a K. And if we look a little bit to the right, to the equal side, we see that geometry, crack size, and stress, these are important things. So if we look at the crack size, we can see that it's right next to the geometry. So there's a very clear link between the geometry of what we test and also how the crack behaves. And to be able to illustrate this a little bit better, we will zoom in a bit and we see what happens at the crack tip. So very simplistically drawn there, we see that we got a brittle crack and a ductile crack. Now the red is the crack, and that blue line or the blue circle, that represents the area in front of the crack. So a brittle crack, it's a straight line. There's not, it's very fast. The energy needed to propagate the crack, to make the crack grow, is not a lot. Whereas if we look at a ductile crack, we see this circle in front, and that tells us that the crack doesn't have a straight path. There are some other things in there that is stopping this crack from growing. And the more work is required to make that crack grow, the higher the fracture toughness will be. Right, now another important concept here is the slide shows 3 examples of how the plastic zone can behave. Because it tells us whether we're looking at linear or non-linear behavior, or whether there's a combination of both. Of course, linear is straight. There's a straight line. The mathematics is easy. If it becomes non-linear, it becomes a bit more difficult. So very quickly, the more red you see, the more difficult it is for the crack to grow, and of course, the more difficult the mathematics become. And again, the geometry plays an important role here. And this is why we've got something called plane stress versus plane strain. And these conditions affect what happens at the crack tip. So under plane stress conditions, we have a large plastic zone. So a lot more energy is required to make this crack grow. And we'll find that thin materials will generally give us a plane stress condition. Whereas if we look at a plane strain condition, the plastic zone is smaller. And this is typically what we see in thicker materials. So to generalize, if we want to test for ductile fracture, we can use thinner materials. But if we want to test for a brittle fracture, then we need to go to thicker materials or a thicker test specimen. Right, go back to this fracture toughness again, this stress intensity factor. So if we add a C to it, KC, then we get something called the critical stress intensity factor. And so not just do we know what the stress is at the crack tip, but we can also find out what stress is needed to make that crack grow, and that becomes the critical part of it. And then as we can see, there's a 1, 2, and 3 there. That gives us the different ways of the different modes of the fracture. So K is our first way to describe fracture toughness. It's our first parameter. It's our first fracture toughness parameter. And in this case, it's linear elastic. So it means linear elastic. What does that mean? It means everything happens in a straight line, and there's no plasticity really. You know, once it snaps, it snaps. You don't go into a lot of ductility and a lot of toughness. So material with high toughness will not necessarily, we won't use this type of testing. Even though K can be part, as we'll see later, it can be part of it. It's just the start. We then need to look at other things, and here we've got CTOD or fracture toughness, the crack tip opening displacement, and it includes plastic deformation that happens before failure. So we have elastic plastic conditions. So the mathematics then has to include both the linear and the non-linear part, as we can see there by those blue boxes. It gives us both behavior. Now another one similar to CTOD is the J, or the J integral. What makes it different is that the way that the fracture toughness is derived is different. For this one, it looks at the energy at the crack tip, whereas crack tip opening displacement, crack tip opening, that more or less looks at the mouth, how the mouth of the crack behaves, where this one, even though it could use some of the similar equipment, it uses the energy under a curve, and the mathematics is different. So just a quick comparison of everything. K and CTOD and J, or J integral, all three give the fracture toughness. Now, the same specimen can be used. We can add instrumentation to all of them to understand what is happening at a very fine detail as the crack propagates. But the key difference is that we've got linear elastic conditions and elastic plastic conditions. In other words, we've got no to very little plastic zone in front of the crack. Then we'll use K, and if there is a good plastic zone in front of the crack, then we'll use CTOD and J. Of course, that's for the elastic plastic crack behavior. Another way to look at this is in a table. There are some, well, there are many similarities, but there are some key differences. As an example, you know, look at the plane strain versus plane stress, or how the toughness is calculated, and also where it comes from. Interestingly, well, if you look at J on the right hand side, it includes the area under the curve. Then for me, which is quite interesting, is we can see that it came from specific needs. So K came from the critical stress intensity factor. That came from ships during the Second World War that were breaking apart. So that then gave birth to that part of fracture mechanics. And then CTOD, crack tip opening displacement, that was the oil and gas. And then they had some good experimental ways to do that. While as the nuclear industry, they relied on numerical methods, but of course it also used the testing part, but their methods were more numerical, and it was for the nuclear industry. So what am I trying to say here? Apart from it being interesting, there isn't one test that fits everything. We have to assess the situation. We have to assess what it is we're trying to do, and then from there we can look at the test specimen, the geometry, and also the type of test, the type of loading, and the type of equipment that we need to attach to do it. And of course, the geometry is important in all of that. Now I'm getting close to the end of the presentation, and I want to introduce you to fatigue. Now, fatigue tells us how many times a load can be applied to a test specimen before it fractures. And luckily we can use the same specimens as before, but for welding we already have something similar to a crack. If we just where the arrow is pointing, the weld toe. So these specimens may look a bit different. But the concepts that we looked at earlier, for K and CTOD and J, those same concepts apply for fatigue, crack growth. The geometry, the crack size, the plastic zone and stress, all of this still applies. And we can just copy that and paste that over. But something new to consider with fatigue is that the crack is going to speed up. You'll either have a phase where there's no crack, and then it will start, and then it will be very fast, and then you'll have your fracture. And it looks at what happens around the crack tip. In that, we've got, if we look at this graph, or this, yeah, let's call it a graph, this curve here, we see there's slow, steady, and fast. And what that tells us is that in the beginning, there's going to be crack growth will be slow, then the crack growth will be steady, and then towards the end, the last phase, it's going to be very fast. And another important thing there is this red arrow, which points at a threshold. Now, what this threshold means is that before this, the crack will not grow, regardless of how many cycles there are. It's just because the stress intensity is not big enough. So this is one of the key things, important things from fatigue, testing for fatigue, fatigue crack testing is that to get an understanding of how it behaves. How does it go through these three phases, slow, steady, and fast? You know, and what is the threshold value? What is the limit that we can set? And say, okay, for this stress, and let's call it stress, for this stress and for these number of cycles, the crack is not going to grow. And that's something that we can derive from testing. Okay, so I think I've come to the end of my slides. Hopefully it was very quick, and it's a big topic, and it's not possible to in 25 minutes or so to put everything in there, but hopefully I showed something new, and hopefully I could introduce you to fracture testing and fracture mechanics. If we have that information, then we can revisit the question that was asked in the beginning. You know, is there a safe way to deal with flaws? Do we just have to stick with the maximum flaw size that is stated in the specs and in the codes, or is there a way around it? You know, what can we do? So what I introduced today is the fracture toughness and fracture mechanics approach. And luckily there is a safe alternative, and I will hand you over to Mads, and he will then be able to tell you more on how we can do that. So Mads, are you there?
Yes, I.
Okay. What I will then do is I will stop my presentation, and all yours. You can take over. And
were we
do
going to
the
have
next
some
present.
questions before I start?
Oh yeah, of course. Eric wanted to have a break, eh? Eric?
Yeah, just does anyone, Rian, I think you might need to mute. Does anyone have any questions that came up from the first part of this session? I know Rian and Mass might be able to pitch in here. If we have anyone with questions, feel free also just to unmute and shout out. We're not that many people, so I think it's okay for us to start a little bit of a conversation as well.
I would actually like to pitch in here. Rian, thank you for the presentation, and I hope you can hear me.
Yeah, Mehdi, I can hear you.
Yeah, on the other side of Denmark. Well, actually, as you covered it quite well yourself, it's a very broad topic, and you managed to give us a very broad look into it. And actually, before this webinar started, we actually got some questions coming in, and I was thinking if you could just take two of those before we move to Mads. And there is one concerning the difference between stress and strain.
Okay. Yeah, I would say a very easy answer would be that stress is what you do to the sample. So it involves the load and the geometry. That's what you apply to it. Whereas strain would then be how that material behaves once the stress is applied. And to make it even simpler, you know, stress is what you do to the material, and then strain is how does that material behave once it feels the stress. So how does it deform? How does it change its structure? That is strain, and stress is what it feels.
So in short, you could say that stress is the loading and the strain is the deformations of the material.
Correct. We also, Mehdi, actually just have a question in the chat now, which is, Rian, is it essential for the mounting points of the specimen on the upper and lower fixtures to have a 90-degree orientation against each other? Does this apply for all geometries? I guess it was something that was shown on one of your slides.
Yes, I would say it does, because it depends on the test. Mads, help me if I say something wrong here. But if we want to just simplify it, what we want to produce is we don't want to introduce something at an angle, because then the application of the loads may not be symmetrical. So from that perspective, it's important that it is 90 degrees. But of course, there will be exceptions depending on the geometry of the specimen, depending on what we will achieve, what we want to achieve. But I would say, in principle, yes, first approach is make sure that everything is aligned.
Yeah, there are different tests for fracture mechanics, so different setups, but most of them they introduce that some kind of bending for the CT specimen or the SENB specimen, and that requires the 90-degree angle in the way that the crack is oriented. So yeah.
So there's a question there from, okay. We have a few more questions. Mehdi, do you want to ask those questions? Can you see them, or shall I do it?
I can take the one for the fracture toughness, if it's better to increase the size of the specimen until getting it through the E399 or to switch to E1820. I would say that sometimes or very often it becomes very difficult to get valid results in the K1C testing at room temperatures or 0 degrees Celsius. When you're going to lower temperatures, then it is more. It becomes more probable that you will actually get a brittle fracture, but at higher temperatures, you will get unreasonable large test specimens that will not be able to fit in many test machines. So I would switch to the E1820 standard and do a CTOD or J-test of the material.
Mehdi, I think for the sake of time, maybe we should move on, since that question came, via email. We can hold it to the end probably, and for the sake of time, we should probably move on and let Mass run through his part.
Yes.
So Mass, why don't you share, and we're looking forward to it.
Will do. Just need to click the right buttons. Yes. I'm going to talk a little about engineering critical assessment. So that is the assessment of floor sizes in structures, and how we can estimate critical floor sizes based on the BS 7910, and also on using actually using fracture mechanics testing to get some more to increase the allowable floor size at least, and to estimate the lifetime of a structure with a flaw. To begin with, just have a short introduction. So flaws are always present in the structures, whether they are welded or non-welded. The acceptance is usually based on quality control. So that's using NDT methods and using some codes that give some acceptance criteria for the flaws that has been found. Usually these codes, they are conservative, so they are based on well, if the flaws or defects or indications are smaller than what we say in the code, then you should not have any problem with the structure in its lifetime. The NDT and the codes, they are valuable to monitor quality during production. So that is just to make sure that the workmanship is actually pretty good for the things you are manufacturing. If you have defects or indications that are larger than what is allowed, there is an alternative to actually assess if this indication is okay or not. And that is the engineering critical assessment, which is a fitness for service based approach. This can allow for larger floor sizes. You may be able to determine the remaining lifetime if you have fatigue loads, so you can estimate the crack growth during lifetime. But again, I would say that this is not an alternative to good workmanship. So if you're starting to have larger flaws than are allowed for the codes, then I would strongly recommend that you revise the production method and make sure that the quality increases, because it is not just a way to say, well, we can do the ECA and then we don't need to make good quality. So keep that in mind. So, engineering critical assessment. If we start to look at the fracture toughness or critical flaw sizes, on the right side of the screen you can see a failure assessment diagram, and here we have the yield ratio on the x-axis and the fracture ratio on the y-axis. This means that we are assessing both for brittle fracture, that is on the y-axis, and then we have the yield ratio, how much of the yielding in the material have we, and this is the y-axis, and it's a combination of the two. The area inside the curve, blue curve, is safe, and outside then we have a risk of a fracture in the flaw size. The red line is actually an estimation of a beginning or a fatigue crack growth. So we start at the bottom and then the crack growth until it reaches the failure assessment diagram. To do these determination of the critical flaw size, we need to do a stress analysis. It can be done by either strain gauge measurements or a fine element analysis. The defect size need to be estimated, and that's usually done by non-destructive testing. We need to know the material resistance, so again we can get that from fracture toughness testing, and fatigue crack growth testing for fatigue crack growth curves. And then we use the BS79 standard to do the flaw assessment, and here we do determine the critical flaw sizes. That's both for fatigue crack growth and for final failure. In addition, safety and failure probability may be necessary to get a result that you can live with in the probability for a failure. So the engineering stresses we use in these assessments, it is usually the structural hotspot stress. We use the membrane and the bending stress based on a linear stress through the thickness. And again, we can do this from fine element or strain gauge measurements. And on the sketch here on the right, you can see here we have 2 points where we have the measured stress, and then we extrapolate into the point of this field weld where we want to find the hotspot stress. And here we have a membrane component, and then we have the bending component, the blue line. Green is membrane, and the blue is the hotspot bending. For a fine element analysis, it could be a tube like this where we have stresses applied, and it's fixed in both ends. And here showing more that the way we estimate the stress is, again, we try to get a path up to the point where we have the geometric change, and then we estimate the hotspot stress in this way. So that's one approach with the fine element analysis. I'm not getting more into the strain gauge, as it is quite similar as you place the strain gauges in certain distances from the, for example, the weld toe, and then you extrapolate again the two stresses into the point where you want to find the stress. Next, we need to know what the initial flaw size is. We know that the presence of a flaw can significantly reduce the life of the component or structure. They may be present from manufacturing, from weld undercuts, for example, or deep machining marks, or voids in the welds. They may also come from operation of the component or structure, and cracks can develop here due to fatigue. And again, the initial flaw sizes are usually determined from NDT, and here it's quite important to know what sizes can you actually, flaw size can you determine from the NDT method with a high enough probability that you will find them. if that is 3 millimeters or 5 millimeters in length. So there's, again, here with the initial flaw size, there's some kind of uncertainty based on what entity method that is used and what is the probability of actually finding a specific flaw size. Material resistance, or the fracture toughness. I'm only going into the K1C due to time restraints. But K1C, or K, is the stress intensity factor, and as Rian also told us, in the linear elastic fracture mechanics, and we assume low plasticity in the crack tip, and therefore we expect a brittle fracture from the testing. The K1C is obtained from fracture toughness tests, and it has this downside that we also talked about here in the questions before, that it often requires quite large specimens to obtain brittle fracture. And the ASTM E399 requires that the thickness B is larger than 2.5 times the K1C divided by yield strength in the power to 2. KQ or K1C, if it's a valid test, is then based on the load that you apply to the at fracture, and or as you can say PQ. If you look at the sketch over on the right, there are different ways that the fracture toughness test can end. One is that we have a little bit of plasticity, so we get some nonlinearity in the curve, and then the PQ is based on the 95% secant line here. If we have a pop-in, so there might be some porosity in the material that actually makes the curve to go a little down, so we get a little bit of a small fast break in the test. Then the PQ is at the top point here, and we have a P5 here at the 95 secant. So they are not equal to each other as they are over here. And then we have the optimal test here, where the PQ is equal to Pmax, where we don't have any pop-in, and we have a very, very small plasticity in the material before fracture. In essence, you can say that the tested KQ or K1C needs to be larger than the stress intensity factor K1, which is equal to the applied stress and the square root of pi and the crack height A, and then a geometry factor F, which is a function of the flaw size and the width of the plate, or geometry thickness of the plate you are looking at. An alternative to fracture toughness test is that you can estimate the fracture toughness from a Charpy impact test. This gives a conservative estimate of the fracture toughness, but if fracture toughness data is not available, or it's not feasible to make fracture toughness tests, you can estimate a fracture toughness from impact tests. It is conservative, but it's, yeah, you could say that it's better than nothing. And it is used quite a lot, especially if it is structures that are already in operation, and you can't get material from that to make fracture toughness tests. And then you may have the impact tests from material certificates and from material certificates. Then we need to know what kind of a flaw we are looking at. And I'll just show a few examples. We have the surface flaws, a small surface flaw on the top. We have a long surface flaw here on the bottom. We have embedded flaws, which are inside the material. These are less critical than the surface flaws, and in my experience, it's they allow for larger fatigue lives, and you can have larger embedded flaws than you can have surface flaws. And then also, if we have some flaws near the weld toe, then we also need to account for that. The flaw location also has an effect on the size of the, or we need to know if it's in the base material or near a weld. And that's one thing is due to that if it's near a weld toe, as I said earlier, we need to estimate the hotspot stress. But also the residual stress is actually, even though the material is operating in a, for example, plus minus 50 megapascals, then due to residual stresses, the material near the weld will actually only have positive stresses. So you have a positive R ratio. And that also affects both your critical flaw size based on the fracture toughness, but also the fatigue crack growth curve if we are going into look into a fatigue crack growth. We need to consider thermal stresses and if there are any misalignment near the flaw. Rian was also talking about this, the fatigue crack growth curves and the 3 regions, or just say that the threshold value is where we don't expect any fatigue crack growth. Then we have a linear relationship between the crack growth and the delta K here in the region 2. And region 3, that's where we get instability and we are close to the fracture toughness in the delta K or the K value, maximum K. I'll go through a few examples and for here, yeah, I've used the BS 7910 recommended fatigue crack growth curve for the as welded condition, and then I made a fictive alternative curve called the tested curve, where I've increased some of the values, both for the threshold value and the curve is a little to the right for the actually to the recommended curve. So it's just to show the difference and the possibility to actually use curves that we are obtaining from testing. The relationship between the fatigue crack growth and the delta K is shown here, where the dAdn is equal to constant A times the delta K to the power of M. And the M is the slope of the curve, you could say. The first example here is it's not on the fatigue crack growth, but more on the critical flaw size. I've taken a long flat plate with a thickness of 20 millimeters and the surface flaw with a height A, which is variable, and the length C equal to 50 millimeters. Material is S355, and the toughness is variable. So what you see here on the right is actually the critical flaw height based on the fracture toughness. The primary bending stress that I've applied to this case is 130 megapascals. The condition is as welded in the secondary stresses, and I've applied some safety factors on fracture toughness and the size of the weld. So as you can see, if the fracture toughness is around 1500 Newton per millimeter in the power to 3.5, we get a critical flaw height of 0.6 millimeters. If we increase to 3000 in fracture toughness, we have 2.5 millimeters. And if we go up to 5000, for example, then as you can see, the critical flaw height actually increases quite a lot. The reason why I'm bringing this example is if we are using the estimation from Charpy impact toughness, we usually will get some values between 2500, maybe up to 3500. But with fracture toughness tests, we might actually be able to get higher values. So again, we can allow for larger defects which are not critical, or we can increase the lifetime of the structure, which we will get onto here in the example number 2. Again, we have a long flat plate, 20 millimeter thickness. I started with an initial surface floor with a height of 0.5 millimeters and a length of 20 millimeters. Material against S355, toughness 4500. Same primary bending stress, and again we are in the as welded condition. And for this example, I've used the BS7910 recommended as welded in air curve, and again I've applied safety factors. The fatigue stress spectrum I've made up here is shown over here on the right, where we have this example is I've estimated that this is a 20-year expected stress spectrum, and the fatigue life here is 1.7 years. So shown here on the failure assessment diagram, you can see for the first iteration, we are down here with the floor size, and the floor increases in size, and then we reach the failure assessment diagram curve, and we have a risk of a failure. Looking at the crack growth, we can see both the floor height increases and the floor length increases until a height of 8 millimeters increased from 0.5 millimeters after 1.7 years. The next example is the same as the one before, but I've used the as tested curve I showed earlier, where we had increased both the threshold and the fatigue curve was a little bit better. But the fatigue life here is increased to 15.4 years. And again, you can see the same failure assessment diagram. There are a lot more points. And again, the crack grows from the 0.5 millimeters to 8 millimeters. This time it's more than 15 years before we reach the critical floor size. Example 4 is similar to the 2 previous ones, but here we are looking at the limit for when fatigue crack growth is actually observed. And for the BS7910 recommended curve, the limit for fatigue crack growth is for a floor size or height of 0.15 millimeters and a length of 6 millimeters. If we increase the threshold value by a factor of 1.5, we increase this limit to a floor height of 0.35 millimeters and a length of 14 millimeters. So in conclusion, you can say that small flaws and defects are always present in the structures. The acceptance and the size of flaws may be increased by using engineering critical assessment. The fracture toughness may be estimated from Charpy impact testing, but are conservative compared to fracture toughness tests. And the BS7910 has standard FCG curves for steel. It's both in air and corrosive environments, and for aluminum. It is possible to use fatigue crack growth curves estimated from tests if you have some more exotic materials, or you want to test at specific R ratios, and you want to challenge the recommended curves in the standard. As I said earlier, ECA may allow for larger defects, but it's not an alternative to good workmanship. ECA may also estimate time to failure of a present flaw. This may be an approach to estimate inspection intervals as well. Thank you for listening. I hope you enjoyed it. Thanks.
Great, Mads. Thank you. I think we have time for 1 or 2 more questions if anyone has anything. We also are making a recording of the session, and we'll make it available to those that have attended today, in case they want to, even just to see the contact details of Mads or me, and if they want to get in touch with any questions later. Does anyone have a question or two before we have to wrap up? Mehdi, what was the other one you had that you wanted to cover quick?
Yeah, well, there was actually one more for Rian, but let's take the one for Mass first. There was a question concerning composites. And the question sounds like this: does the work also apply for composites?
Don't have much experience in composite materials, but I do know that there are some test methods for composites, and I've stumbled upon some articles on also on fracture toughness for composite materials, but I must be honest that I do not have any experience with it myself.
Okay.
But this is basically primarily for metallic materials, what I've been covering.
Perfect. Maybe we can get this answered by one of our colleagues.
Yeah, well,
specializing in that area. Yeah, and then there was that last question for Rian. Rian, are you still there?
Yeah, I'm here.
Yeah, and this is also not concerning metallic, but it's does glass have fracture toughness?
Well, my first answer is to say no, because it's brittle. But of course, if you laminate glass, then you can give it fracture toughness. Mass, what's your take on this? Can glass have fracture toughness?
I would guess so, but I'm not sure.
But there is a numeric way, you know. I think that's how fracture toughness sort of started, by looking at brittle materials. So maybe there is something mathematically it can be shown.
Okay.
but I think if we get back to the core of, Rian's and Mass's presentations, we were looking at an application within metallic materials. For those maybe that are working with other materials in other, that in their daily business, we do have specialists also within areas of composites and plastics and glass. I have to check, to be honest, but we have a number of specialists in other areas as well, where our testing capabilities, the physical infrastructure, can be used for different sets of materials. So for those that might be interested in working with different sets of materials and use them on a daily basis, please feel free to get in touch, and we can also connect you with our specialists in those areas. But I do see we're out of time now, so I would like to say thank you very much to everyone that attended, and as well, Mass and Rian, thank you for the great presentations. And again, if anyone has any questions after the session, please feel free to get in touch with any of us, myself, Rian, Mass, Mehdi, and we'll make sure we get you an answer to your question. Okay, thank you very much, and have a great afternoon, everyone. Bye.
Thank you. Bye.